We now come to enumerative combinatorics. As with some other parts of this course, this is really a whole field and a pretty vast field. By now, there is dozens of books about it. In particular, I'd like to mention Stanley's encyclopedia. So Stanley's Enumerative Combinatorics, it has 2 volumes. I recommend it particularly because it has a lot of problems, some of them pretty challenging. So if you like enumerative combinatorics, that's where you can find a lot more to mull over. But for now, let me just show the basic principles and again, a few applications of them. So some of them we have already used. Here is the bijection principle. Let X and Y be 2 sets. Then the sizes are equal if and only if there exists a bijection from X to Y. Next, the sum rule. If S1 and so on S to K are disjoint finite sets, then as their union is also finite, and its size is the sum of the sizes of the S's. And if you do not require them to be disjoint, then it will be a lesser equal, not an equal. So here is the product rule. It's pretty similar, except instead of union, you have a direct product, a Cartesian product. And here you have a product. And you no longer need disjoint. So if A1, A2, and so on, AN are finite sets, then their Cartesian product is also finite and satisfies that its size is the product of the sizes. Next, the power rule, which is really a particular case of the product rule. If A is a finite set, and if n is a non-negative integer, then the size of A to the n is the size of A to the n. So A to the n, this is, and I can also say that it's finite. So A to the n, it's the set of all n tuples of elements of A. It's the Cartesian product A cross, and so on cross A n times. Next, the difference rule. If A is a finite set, and if B is a subset of A, then the size of A without B is the size of A minus the size of B. This follows from this rule because A without B and B are disjoint and their union is A. So these things are, in my opinion, pretty common sense, but we can do a lot just using them.